This plastic sheet is a piece of Polaroid. We can look through this sheet out at the graying snow outside. If we put another sheet of Polaroid behind the first one, the image gets lighter and dimmer depending on the orientation of the sheet. If we orient the second sheet like this, the sunlight will come through and we can see outside. But if we rotate the second sheet until it's perpendicular to the first sheet, the light gets dimmer until no sunlight goes through at all. What if we put another Polaroid sheet between the two sheets at an angle? We can see the snow again. So why does this happen? Electricity is used to push charges around. Light is an electromagnetic wave, which means it too can push charges around. When light hits an object, the object can absorb the light, which pushes on the electrons in that object, causing them to jiggle. In doing so, some of the light's energy is given to the electrons. This property of light, to push electrons around, is called its electric field. Incoming light from the sun or a fluorescent lamp bulb has an electric field that can push free electrons in any direction. However, in some materials, like our Polaroid sheet, electrons can only be pushed in certain directions. Polaroid is made of long chains of molecules that are lined up parallel to each other. For the most part, electrons inside the Polaroid can only jiggle in the direction along the molecules. When light strikes the Polaroid, only the light that pushes in the direction of the molecules gets absorbed, while the rest of the light can go through. For example, imagine that the electrons in this Polaroid sheet were aligned horizontally. If the light that struck the sheet had an electric field that could only push in the horizontal direction, all of that light would be absorbed by the electrons to jiggle them back and forth. Thus, you would not be able to see through the Polaroid. Now imagine if the light that hit the sheet had an electric field that could only push in the vertical direction. The electrons in the sheet would not be able to absorb this light because they can only move horizontally. Thus, this light would go through the Polaroid. What if the light that hit the sheet had an electric field that pushed electrons diagonally, neither completely horizontally nor completely vertically? Well, if the light struck free electrons, those electrons would be pushed diagonally. It's as though the electron moved both horizontally and vertically. Imagine dragging a box across the floor with a rope. If you pulled it parallel to the ground, it would move towards you. If you pulled it perpendicular to the ground, it would lift off the ground. If you pulled it diagonally and you were really strong, it would lift up and move towards you. But if the box were too heavy, it would only move towards you. Thus, we can see from this example that when an object is pushed, it does not have to move in the same direction as it is pushed. Similarly, light with the diagonal electric field pushes both horizontally and vertically. The electrons in the sheet are restricted vertically, that is, they're too heavy to lift, but they can be moved horizontally. Thus, electrons only absorb the part of the light that pushes horizontally. The vertical component of the light will be able to go through the sheet. The light that enters the sheet was pushing diagonally. The light that exits the sheet is only pushing vertically. It's as though some of the light was absorbed, and the rest of it was rotated. When we looked through two Polaroid sheets, we couldn't see through them when the molecule chains in the second sheet were oriented perpendicular to the first. The light that comes out of the first sheet is perpendicular to the electrons jiggling in the first sheet. When that light hits the second sheet, all the light that is polarized parallel to the molecule chains in the second sheet is absorbed. When the second sheet is oriented perpendicular to the first, by simple geometry, the second sheet will absorb all the light that comes from the first sheet. That's why we can't see through the two sheets. Thus, all the light that emerges from the Polaroid has an electric field that pushes perpendicular to the vibrations of the electrons. Light that pushes in the same direction is called polarized light. So why was it that we could see through the three sheets when we couldn't see through the first two? Let's trace the polarization of light through the three Polaroid sheets. The incoming sunlight has an electric field that can push electrons in any random direction. When this light hits the first sheet, the component of the light that pushes parallel to the electrons in the Polaroid is transferred to the electrons, causing them to jiggle in one direction. The rest of the light goes through to the second sheet, which is tilted so that its molecule chains are neither parallel nor perpendicular to the first sheet. The light that hits the second sheet pushes the electrons in a certain direction, but the electrons can only move diagonally. Just like before, the component of the light that pushes along the molecules will be absorbed and jiggle the electrons in the sheet. Only the light that pushes perpendicular to the sheet can go through, so the light that exits the second sheet is pushing diagonally, even though the third sheet is perpendicular to the first sheet. The light hitting the third sheet is no longer pushing in the direction of the first sheet's molecules, so it won't all be absorbed. The second sheet absorbed some of the light and rotated the rest. When the light finally reaches the third sheet, the light is again pushing electrons diagonally, so only some of it will be absorbed, while the rest can go through.